let's start today's session. We are going to continue our discussion with respect to decision tree, one of the machine learning algorithms. As I stated earlier, decision tree can be used as the classification algorithm or regression algorithm, but typically, most popularly, it is being used as the classification algorithm. And we are going to discuss this decision trees as the classification algorithm. So, as I stated earlier in the last session, we are going to discuss decision tree algorithm, which is known as ID3 algorithm. This is the basic algorithm for decision tree. ID3, ID stands for Iterative Dichotomiser algorithm. So ID3 algorithm that we are going to discuss next. We are having, in fact, few more algorithms. Those will help us to build the decision tree. So other than ID3 algorithm, we are having C4.5. That is one more algorithm. It is the successor of ID3 algorithm. And also we are having one more algorithm, that is classification and regression tree algorithm, CART algorithm. So in this course, we are not going to look at these algorithms, but we'll be focusing upon the basic ID3 algorithm that has been popularly used. So there are three important steps in our ID3 algorithm. This ID3 algorithm is typically meant for selecting a node, decision node, right? So while building a decision tree, if you remember how our decision tree looks like, we are having the root node, then depending on the values, root node is the decision node and that contains some attribute. Depending upon the criteria or the value of that attribute, say for example yes or no, we are having two different branches here, one branch for yes, another branch for no, and based on that we'll be selecting some other attribute further, and based on this attribute value we are going to further expand our decision tree. And the leaves actually are denoting the class. So these are the leaves. Leaves are the nodes which are not having any children, right? So these are the leaves, and leaves in the decision tree actually are giving us the class of the sample. So we begin from the root node, and based on whatever is the attribute or the feature that is under consideration at the root node, we go on following a particular path till we reach to the leaf node, wherein the leaf node will provide us the class of that particular sample, right? So what is important is, for a given training data set, we should come up with such kind of a decision tree. So we need to select appropriately the nodes, decision nodes, right? So which will be the root node? What would be the next node under that root node? So the decision nodes to be selected properly, and there is some criteria how to select the decision nodes. And one of the algorithms to build such kind of a decision tree is the ID3 algorithm. So ID3 algorithm requires some statistical computations based upon the training data set that we are having. So let us go through the algorithm first, and then we'll demonstrate you one example, right? How to build the decision tree. So we are having three important steps in our decision tree algorithm. What are those 3 steps? In the first step, we are going to compute the entropy for the training data set that we have. And let us assume that the training data set is denoted as S. So in the first step, we are going to compute entropy of, yes.
What is meant by entropy here?
I'm going to demonstrate you. Please listen. Let us go through the algorithm and then I'm going to explain everything.
Okay.
So we are going to compute the entropy for data set, given training data set. So here we are assuming that S is the data set. So we are going to compute the entropy of this data set. We are having the mathematical formula to compute this entropy. I'm going to explain it a bit later, right? But this is the first step, computation of entropy for data set S. For every attribute or for every feature in our data set, we are going to apply these steps, right? So we are going to pick the first attribute, and what we are going to do is we are going to compute once again the entropy for all attribute values, and we are going to denote this entropy like entropy. A is the attribute and V is the value of that attribute. Say for example, if I am having here some attribute, and for that attribute, if I am having 2 possible values, y and n, then I'll be computing the entropy for this attribute for value y also, and I'm going to compute the entropy for the attribute for n value also. So this is how we are going to pick one attribute and we are going to compute entropy for all attribute values of the selected attribute. What next? Next, we are going to compute average information entropy for the current attribute. And here we are going to consider all the attribute values. So if a particular feature or a particular attribute is having 2 values, yes and no, then for every value we are going to compute the entropy, and based on those values we are going to find out the average information entropy. I am going to demonstrate all the mathematical formulae that we are going to make use of. In the third step, we are going to compute the gain for the current attribute. So this is actually the important parameter that we are going to compute, gain. So for that particular selected attribute, we are going to compute the gain, right? Once again, we are having the mathematical formula. I am going to discuss that. So after computing the gain, we are going to iterate this step number 2 for every attribute. Say for example, if I am having 4 attributes, for every attribute I am going to compute the gain, right, by making use of this step number 2. And in step number 3, I'll be listing out the gains for all the attributes. Those are computed in step number 2, and then I'll be picking up the attribute which is having the highest gain, and that will be my decision node, right? So the attribute having highest gain will become my decision node, and the similar procedure is being iterated until our decision tree is built, right? So obviously we should have some stopping criteria where to stop building the decision tree. So our stopping criteria is like if all the examples belong to the same class for at a particular decision node, then we are going to stop. Or if there are no more attributes to test, we are done with all the attributes in our data set, then also we are going to stop. I'm demonstrate now this algorithm with the example so that you can understand it better, right? But you should have a note of all those steps of ID3 algorithm. Now, what is entropy? So, entropy is actually representing the impurity of an arbitrary collection of examples. I'm saying entropy is actually representing impurity. So what we mean by that impurity or purity of an arbitrary collection of examples? So in fact, the mathematical formula that helps us to compute entropy is like entropy of data set S is given as summation over I equal to 1 to C minus pi log of pi to the base 2, where this C is the number of classes that we have. So if I am having 2 classes, then the value of C will be 2. If I am having 3 classes, this value of C will be 3. So what is C? C is the number of classes that we have having. Okay. Now, what is this Pi? Pi is the probability. Pi is the probability of class I equal to 1. So P1 is the probability of class I equal to 1. P2 would be the probability of class I equal to 2 and so on. So Pi in general is the probability of class I equal to class I, right? And how actually this entropy helps us? If I am having all the samples in a particular data set, if I am having all the samples in the particular data set with same class, then obviously my entropy is 0. So my data set is very pure. What does this mean? If I am having the data set wherein I am having 10 samples, and if all these 10 samples belong to the same class, then the entropy would be 0. Right? If I am having the samples, those are distributed in equal number. So if I am having 2 classes, positive and negative, and if I am having equal number of positive and negative examples in my data set, then I'll say that my entropy of the data set is 1. So entropy is 1 when the collection contains equal number of positive and negative examples. And if the collection contains unequal number of positive and negative examples, then the entropy lies between 0 and 1. Right? So minimum entropy is always 0, maximum entropy is always 1. So when entropy is 0, if all the samples belong to same class, then entropy would be 0. If we are having equal number of positive and negative samples, then entropy will be 1. And if we are having unequal number of positive and negative examples, then our entropy will lie between 0 and 1, right? Any fraction. So if pictorially we can look at, we can see here that if I am having all the samples, those belong to say class 0, or all the samples, those belong to class 1, then my entropy would be 0. All samples belong to either class 0 or class 1. If I am having 50% of the samples, those belong to class 0, and 50% samples, those belong to class 1. That means equal number of positive and negative samples. Then I'll be having the entropy that is equal to 1. Okay, and in between, so if I am having few samples, unequal number of samples, those belong to class 0 and class 1, I'll be having the entropy in between 0 and 1. So this is how we can pictorially show. the relation between the number of examples belonging to a particular class in the data set and the entropy of the data set. So how we are going to compute this entropy? This entropy is being computed by making use of this formula. So summation over I equal to 1 to C minus Pi log of Pi to the base 2. So entropy basically determines the purity of an arbitrary collection of examples. We may say that our data set is pure if all the samples belong to the same class. Impurity is actually if we are having the mix of samples having different classes, right? So I hope you must have understood what we mean by entropy and how to compute the entropy. Now let us go through the example to demonstrate how to select the node, decision node, right? Now this is our training data set. So what we would like to do is we would like to create a decision tree to predict whether tennis will be played on the day, right? What we want, this is our example for demonstration. We are having a data set with 14 examples in the training data set. We are having 4 features: outlook, temperature, humidity and windy. These features are actually demonstrating the weather of the day. And based on this weather condition, we would like to predict or we would like to determine whether to play tennis or not. So play tennis is the target attribute or the decision. So based on the weather conditions of the day, we are going to predict whether to play tennis or not on that particular day. So the class labels that we are having are yes and no, right? So play tennis is actually the attribute which is dependent attribute, target attribute, and we would like to predict whether to play tennis or yes or no. So class labels in our example are yes and no, and these 4 are the attributes those we are having. So in this data set we are having these 14 samples. So sample 1 determines the data for day 1, day 2, day 3 and so on, right? So day 1 weather can be represented, say for example, as outlook sunny, temperature is hot, humidity high and windy. There are windy attribute is having the value weak, that means weak wind is there. Okay, and if this is the weather condition, then we are not going to play tennis, so label is no. So similarly, we are having such kinds of 14 examples in our data set. If we look at this data set, we are having 9 samples with class label yes, and we are having 5 samples with class label no, right? Every attribute is having some values. Say for example, here outlook is having 3 different values: sunny, overcast and rainy. Temperature is also having 3 different values: temperature is hot, mild and cool. Humidity is having 2 different values: high and normal. Windy is also having 2 different values: weak and strong, right? So this is how we are describing our data set. Okay, so let's proceed now with step number 1. In step number 1, what we need to do is we need to compute the entropy for the entire data set. So as I stated, S is our data set, okay, and we have seen the formula to compute entropy. So entropy S is given as summation over I equal to 1 to C minus Pi log of Pi to the base 2. So Pi is the proportion of S belonging to class I. So it is a probability. Pi is the proportion of S belonging to class I, and C is the number of different values for target attribute. So number of classes. C is number of classes. Okay, so this is how we are going to compute the entropy. Then in step number 2, we are going to calculate average information. So just I am giving you the formula to compute average information, and then we are going to apply this for our running example. So information for attribute A is computed as the summation over V belongs to values of A. What does this mean? See, whatever is this quantity, that quantity is being computed for every value of attribute A, right? So for every value of attribute A, we are going to compute SV divided by S into entropy of SV. And finally, we are going to have summation of all those computed quantities. And this will give us the information for that attribute. So values in parenthesis A is the set of all possible values for attribute A. And for every such value of attribute A, we are going to compute this quantity. So SV is the subset of the training data set S, for which attribute A has value V. I'll repeat, what is SV? SV is the subset of S. S is our entire data set. So SV is the subset of S for which attribute A has value V. Right? So for every attribute value, we are going to compute, we are going to find out the subsets, and we are going to compute this quantity. And finally, for every value of the attribute, whatever is the computed value, we are going to sum up all those values to come up with this information for attribute A. Right? And then we are going to compute the information gain. So you please note down these formulae. These are very important, and we are going to make use of this formulae in our further computation. So while computing the information gain, what we are going to do is simply we have computed entropy of S. So this is the entropy of the original collection S, that is the data set. Information A is the expected value of the entropy after S is partitioned using attribute A. So we have computed this information for attribute A also. So after having this difference between entropy of S and information of A will provide us the gain. So gain S comma A represents the expected reduction in entropy caused by knowing the value of attribute A. So whenever we are saying we are going to compute information gain, we are going to make use of this formula to compute the gain for attribute A. And for every such attribute in our data set, we are going to compute this gain. And in step number 3, what we are going to do is whatever are the gains computed for all those attributes, we are going to pick the maximum gain, and whichever is the attribute having maximum gain, we are going to pick that attribute as the decision node. Right? So this is how we are going to compute these quantities. So let's begin with our example. So in our example, we are having 14 different examples. We are having 4 features, and we are having play tennis as the target attribute. And for this target attribute, we are having 2 classes, yes and no. So in the first step, we are going to compute the entropy for this entire training data set. So in the given set S, we are 9 samples with class label yes, and we are having 5 samples with class label no. And we know the formula for computing the entropy for the data set S. So this formula is summation over I equal to 1 to C minus pi log of pi to the base 2, right? So how we are going to make use of this data set and the statistics that we have to compute this entropy S? Let us look at how we are computing it. So entropy S is being computed as, how many classes we have? 2 classes, yes and no, right? So for class I equal to 1 say yes class, and class I equal to 2 say no class. Okay, now we are computing this pi. What is this pi? This is the proportion, this is the probability. So how many samples we have for class 1 or class yes? 9 samples, right? 9 divided by total number of samples, 9 plus 5, that is 14 samples. Okay, so what we have here is minus 9 divided by 9 plus 5. So what is this? This is my P1. Class 1 is say yes class. Okay, so class 1 is yes class. This is my class 1 and this is my class 2. So for class 1, this pi or P1 would be 9 divided by 9 plus 5. So 9 divided by 14. So minus 9 divided by 14. Log of, once again pi we have, so 9 divided by 9 plus 5 to the base 2. Please remember we are having here the logarithm with base 2. Minus, for second class now, so this 5 divided by 9 plus 5 is meant for class 2. So this is P2. Okay, so 5 examples, those belong to class 2, that is no, and total number of samples 9 plus 5. So minus 9 divided by 9 plus 5 log of 9 divided by 9 plus 5 to the base 2 minus 5 divided by 9 plus 5 log of 5 divided by 9 plus 5 to the base 2. So after computation, right? So after computation, we are getting this entropy of S as 0.940286. Right? So this is how we are going to compute entropy of data set S. So this is the step number 1. We have computed now entropy of the data set S. Now we are going to compute information for every attribute. So how many attributes we are having? We are having 4 attributes. Which are those 4 attributes? Outlook, temperature, humidity and windy. So for all those 4 attributes, we are going to compute the information. So let us pick first this first attribute, say outlook. Okay, and this outlook attribute is having 3 values: sunny, rainy and overcast. Right? And we are having this formula with us to compute the information of attribute A. So we are now going to compute information for outlook. Right? Information for outlook. So if we want to compute information for this attribute outlook, what we need to do is we need to compute the entropy for all these 3 values of outlook. So we need to compute entropy So what we need to do is we need to compute the entropy for value sunny, we need to compute entropy for rainy, and we need to compute the entropy for outlook value overcast. Right? So let us see now how we are going to compute these individual entropy values, and then how we are going to compute this information for attribute outlook. Okay, so this is our data set, and we have selected attribute as outlook, right? So my attribute under consideration A is outlook. Now outlook is having three values: sunny, rainy and overcast. So simply what I'm going to do is, I'm interested in only this column because I'm dealing with this attribute right now, and I'm interested in this play tennis, that is the target attribute class. Okay, so we are going to consider these two attributes now, outlook and play tennis. So I'm going to filter out this data set now. So I'll be having now this subset of the entire data set, for which my outlook value is sunny. So I'm having 5 examples in my data set wherein I am having the value of outlook is sunny, and these are the respective labels. These are the respective class labels, whether to play tennis or not. Similarly, I'll be finding out the subset where my outlook value is rainy, and I'm also finding out the subset of the data set where my outlook value is overcast. So these are the examples in each category. So I am having these three subsets now. In the first subset, I'll be having the outlook value that is sunny. In the second subset, I'll be having the outlook value that is rainy. And in the third subset, I'll be having outlook value that is overcast. Okay, along with the respective labels. So what I want now is, I want to compute the entropy for outlook equal to sunny. I want to compute entropy for outlook value equal to rainy, and I want to compute the entropy for outlook value overcast. So how am I going to do that? So outlook is having three different values, right? Now how many samples for sunny? So this subset, how many samples are there belonging to class yes? 2 samples. And how many samples are there belonging to class no? For sunny, 3. Similarly, for rainy, we are having the samples, 3 samples with class label yes and 2 samples with class label no. For overcast, all 4 samples are having class label yes and 0 samples with class label no. Right? So this is what we have. Now based on this data, we are going to compute the entropies. So entropy for outlook equal to sunny. So we are making use of the same formula. What is our formula for computing entropy? We are having the formula to compute the entropy of S, that is equal to summation over I equal to 1 to C minus Pi log of Pi the base 2. Okay, so we are making use of the same formula. So see here, minus, what is this 2? We are having 2 classes, yes and no, correct? And we are computing the entropy for sunny. For sunny, we are having total number of samples 5 for value sunny. Okay, out of these 5, 2 belong to class yes. So minus 2 divided by 5 log of 2 divided by 5 minus 3 divided by 5 log of 3 divided by 5. Please note here we are having logarithm to the base 2. Okay, so this is for class 1, this is for yes class, and this is for no class. So 3 samples belonging to no class out of 5 samples. So if we compute this entropy for outlook equal to sunny, the value comes out to be 0.971. Similarly, we are going to compute now outlook entropy for outlook equal to overcast. So here once again, how many samples we have for class 1? 4 samples. So 4 divided by total number of samples 4. So 1 minus 1 log 1 minus 0 log 0. So this comes out to be 0. Okay. For entropy outlook equal to rainy, we are having once again minus 3 divided by 5 log of 3 divided by 5 minus 2 divided by 5 log of 2 divided by 5. So once again the entropy for outlook equal to rainy is 0.971. So entropy for outlook equal to sunny is 0.971. Entropy for outlook equal to rainy is 0.971 and entropy for outlook equal to overcast is 0. We have computed the entropies for all the values of the attribute under consideration. So we are talking about the attribute, first attribute, that is outlook, right? And for all the values of the outlook, we have computed the entropies. What next? Once we have computed the entropies, we are going to compute now the average, information for attribute A. So we are having this formula for computing the information. So see here how we are going to compute information for outlook. So information for outlook is equal to summation over V that belongs to values of A. So we are having 3 values of A. So values of A is the subset that contains the values for this attribute outlook. So sunny, rainy and overcast are 3 values, right? And next our formula is SV by S, entropy of SV. We have computed all those entropies in the previous slide. Now S sunny. So the first value is sunny. So S sunny. How to compute this S sunny equal to? So how many examples we have for this value sunny? We are having 5 examples. 2 belonging to yes class and 3 belonging to no class. So total number of samples for value sunny is 5. S rainy equal to 5 and S overcast equal to 4. Right? And capital S, that is the total number of samples in our data set. 9 belonging to yes class and 5 belonging to no class. So total number of samples are 40. So these are the values of SV and S. So this is S sunny, S rainy, S overcast, and this is capital S. Right? And we have computed entropy values for all those different values of the attribute. So we have computed entropy, outlook sunny equal to 0.971, outlook rainy equal to 0.971, and entropy for outlook equal to overcast equal to 0. So we are having these values with us. So just by substituting all those values in our formula, what we are going to get is, see here. So this is SV. So this is my SV for value sunny, 5 divided by S 14 into entropy for outlook equal to sunny, that is 0.971, plus once again for rainy, S rainy divided by S into the entropy for rain, plus for overcast now, so S overcast divided by S into entropy that we have computed for overcast. So after substituting those values, the information for outlook that we are getting is 0.693. Okay, now we are going to compute gain, right? So how we are going to compute now gain? We know the formula for computing the gain. We are computing the gain for attribute under consideration, that is outlook. So gain S comma outlook, attribute under consideration is outlook. So entropy S minus information outlook. Entropy S that we have computed earlier, it is 0.940 minus this information of outlook that we are computing is 0.693, and this is how the gain for attribute outlook comes out to be 0.247. Gain for outlook comes out to be 0.247, right? So this is how we have obtained the gain for attribute outlook. We need to follow the same steps for all the attributes in our data set. What we mean by that? See, we are having this data set, so we are done with this outlook. Now the second attribute that we need to consider is temperature. So for temperature also, we need to find out the gain following the similar steps. So for temperature, once again, three different values we have. So we need to find out the subsets, right? Having these three values for temperature, and then we need to compute the respective entropy values for all the different values of temperature. So entropy for temperature equal to hot, entropy for temperature equal to mild, entropy for temperature equal to cool. So this is how we should compute all those values for temperature. Based on these values and following the similar steps, we need to compute information for attribute temperature, right? Information for attribute temperature. We are following the same steps, okay? And information for temperature comes out to be 0.911. So we need to compute now gain for temperature, and it comes out to be 0.029. So this is the gain for attribute temperature. Similarly, we need to compute for humidity, right? And we need to compute it for windy, because we are having four attributes. Okay, and after computing these gains for four attributes, in the last step of our algorithm, what we are going to do is we are going to list out the attribute and the computed gain. So outlook is having gain 0.247, temperature is having the gain 0.029, humidity is having the gain 0.151, windy is having the gain 0.048. So out of all these four attributes and the respective gain values, we identify that attribute outlook is having the maximum gain. Right? Outlook is having maximum gain. So this outlook attribute we are going to select as the root node for our decision tree. Right? So attribute output will be the root node for our decision tree. So in our decision tree, we are selecting this outlook as the root node, and we know there are three values for the outlook, right? Sunny, rainy, and overcast. So we'll be having three branches. So now in the next iteration, what we are going to do next is we need to identify the attribute here as the decision node. So the similar procedure we are going to follow. The similar procedure we are going to follow to come up with these nodes, these decision nodes. Okay. Now, as I stated, we are going to continue this process till we get the complete tree. Okay. Now, see here, Outlook is our root node that we have identified, and we are having three values: sunny, overcast and rainy for Outlook. And what we find is, for Outlook value overcast, if you remember our earlier data, for Outlook value overcast, all the samples belong to yes class, right? For Outlook value overcast, all the samples belong to yes class, right? So we are having the conclusion in this case that for value of Outlook overcast, as all the samples belong to yes class, we will have here the leaf node that denotes the class label yes. But for sunny and rainy, we are having mix of labels, mix of data belonging to both the classes. And that is why we need to iterate through for finding out this decision node and this decision node. And we need to apply the same algorithm. And ultimately, we reach to these leaves wherein it is possible for us to identify the class of the sample. So once we build this kind of a decision tree, how we are going to predict whether to play tennis yes or no. Suppose I am having a test sample. Suppose I am having a test sample wherein say Outlook value is sunny. Okay, humidity value is say normal, windy is say weak, and temperature is say cool. Suppose, okay, here we are not making use of this temperature as the decision node because it is not required in this example considering the data set. So if I am having this as the test sample, then I'll begin from the root node. So Outlook value is sunny, so I will choose this path sunny. Then I'll arrive at this decision node. So I'll check what is the humidity, whether it is normal or high. So humidity value for the test sample is normal. So I'll be picking up this branch, and this branch will lead me to the leaf node wherein I am having the class label that is yes. So if Outlook is sunny and humidity is normal, then I can play tennis. So my prediction would be yes. So this is how we are going to make use of this decision tree. Right? Is there any doubt? Yes? Is there any doubt?
Ma'am,
Yes.
how do you predict the second decision tree, humidity and windy, from the outlook, that is the child nodes of root node?
See, we are going to follow the same algorithm. So we have selected the outlook. So remaining three attributes we are having, humidity, temperature and windy. Right? So for these three attributes, now once again we need to follow the entire procedure. We need to compute. Now see here, for outlook, under outlook, if we select humidity as the attribute out of the remaining three attributes, right? Then for this humidity attribute, we need to compute the entropy, we need to compute the information for every remaining attribute, right? Whatever is the subset here of this data set, we need to compute the entropy for this subset. We need to compute if we select humidity, and if humidity is having two values, then for humidity two values we need to compute the entropy, we need to find out the information, we need to find out the gain for humidity. Similarly, we need to compute the gain for temperature. We need to compute the gain for windy. And whichever is the highest attribute having highest gain, we need to pick that attribute here. So the same procedure, in fact, we need to follow for the remaining attributes as well, so that we can reach to, or we can build this tree. And the stopping criteria, as I stated, the stopping criteria, this is the stopping criteria. What is this stopping criteria under outlook value overcast? All the samples in this subset are having the same label. So that is one stopping condition. So here I can stop, no further branches. I will arrive at the leaf node. And other condition is, if I am exhausted of all the attributes, I have tested all the attributes, I have used all the attributes, then that is also my stopping condition.
No, ma'am.
Okay, so let's conclude today's session. I'll focus upon few more important tips while building the decision tree in the next session. Okay, so thank you.